Hello, my name is John Frensley, and we're going to go over the AP Physics 2 algebra-based free response questions for 2025. This is a service provided by World's Finest Physics. Here's our website. We offer two main services, tutoring for students and professional development for teachers. So if you are a math or physics student or math and physics teacher, there's something here for you at, at findphysics.com. And we're also going to try and start putting up free resources for both teachers and students, mostly for students, on that website starting in the next school year. All right. So it's 2025. They just gave this exam, and let's see what we got going on here. Very long wire 1 carries current I in the positive x direction along y equals 0. Very long wire 2 carries current I in the positive x direction along this line y equals d. Point P is located along wire 1 at the origin. The diameters of the wires are small compared to the distance between them. They're in the xy plane. All right, before I get started, I am going to tell you that this is the first time I've seen these. I've not looked through these before, so I'm going to try and speed run them, but if I make any mistakes, please feel free to mention them in the comments and correct them. Okay, complete the following tasks in figures 2 and 3 using either arrows or the symbols shown in the box above the figures for your response. Okay, indicate the direction of the magnetic field from wire 2 at point P. Okay, so the magnetic field due to wire 2, we're going to take wire 2 in our minds, we're going to pull it out of the page, we're going to put our thumb in the direction of the current of wire 2, and as we curl our fingers, we'll notice that the fingers go into the page at point P, goes into the page. So we're going to use X for into the page, the magnetic field from wire 2 at point P, and then the magnetic force on wire 1 by wire 2. Okay, so wire 2 is creating magnetic field that is dot, 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 X, 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 okay? All right, it's like a really bad store right there, okay? So what we're going to say here is we're going to say that the magnetic field is out of the page. Now, when I do force with my students, I do the gun rule. So this is my right-hand rule where this is the motion, the charges, current or velocity if it's an individual charge, the magnetic field, which can swivel, and then the force. The force has to be perpendicular to the motion, current or velocity, and to the magnetic field direction. So as I turn the page, what I have is I have an end of the page magnetic field, and the current, which is that way, is in that direction. So the thumb tells me that the force is going to be that way. When I rotate the page back, the force is up. So the magnetic force on wire 1 by wire 2 is up. Okay. Very long wire 3 is carrying current 2I in the positive x direction and is placed in the xy plane along the line y equals y3. Do we have a picture for that? Y equals y3. No? Okay. Um, the net magnetic force exerted on wire 1 by the currents in wires 2 and 3 is 0. Oh, okay. Derive an expression for y3 in terms of d. Okay, so all of these are in the positive x direction. So what I think is I think this. I'm going to call this the pink wire right here. Okay, so the pink wire had current that way, okay, and made this magnetic field. Now, I think that wire 3 has to be up here because wire 3 is going to create dot, 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 dot. Oh, nope, 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 nope. I take it back. I take it back. I take it back. No, 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 no. Wire 3 is going to be down here, and this is going to be Y3, okay? And this is going to be dot, 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 X, 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 X. So the dots and X's add to 0. So Y3 has to be down here. And I'm going to say this. This is the basic principle that I'm going to say here. The basic principle I'm going to say here is the B along wire 1 due to the other wires must cancel to 0. So the B on y equals 0 by wire 2 has to equal the B on y equals 0 by wire 3. Okay, so the two magnetic fields. So this is mu naught. This is I because the wire 2 carries just a current regular I. Okay, over 2 pi his distance d, and then this will be mu naught 2I over 2 pi times y3. Well, everything cancels out. Everything cancels out except for this, where you're going to find out that y3 is equal to actually negative 2d, and the reason why is because wire 3 must be below wire 1 for the forces to cancel. So here's the question. I'm assuming that negative actually had to be in the answer. I wonder if that's the case. Wire 3 is moved very far away from wires 1 and 2. A circular conducting loop in the XY plane is initially held at rest below wire 1. The loop is then moved at a constant speed in the negative Y direction. So we're going to take this loop and he's going to go bye-bye, okay? Is there a clockwise or counterclockwise induced current? Okay, so we said before that we're going to have dot, 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 x, 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 due to the pink wire. And then now due to the green wire, we're also going to have dot, 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 x, 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 okay, because of the way it's pointing the same direction, right? So as this loop moves away, what's going to happen is that the x flux decreases. The x flux, the end of the page flux decreases. Okay, so I'm going to go ahead and start my justification here. The magnetic flux through the loop is into the page and decreasing, right? So the loop will create its own magnetic field also into the page to oppose the end of the page flux decreasing. So this is called Lenz's law, and it's a very, very tricky idea. The idea that the loop is going into less and less and less into the page magnetic field. So that means he is going to create his own into the page magnetic field through the action of his induced current. So his induced current is going to create his own into the page magnetic field to try and oppose the decrease, oppose the change. So he's going to create his own. Only a clockwise current can produce into the page magnetic field through the loop, right? Okay, so it is going to be a clockwise current, and it's because of Lenz's law, which is a very, very, very tricky and difficult idea. Okay, so there you go. That was number 1. Let's look at number 2 now. Okay, a sample of monatomic ideal gas is sealed in a thermally conducting container by a movable piston, mass M, area A. The container is in a large water bath that is held at a constant temperature. Okay, the piston is free to move with no friction. The gas in thermal equilibrium with the water bath. The piston's at rest. The gas has a V naught, and the pressure of the air above the piston is P atmosphere. Okay. Okay, the gas, the thermal equilibrium with the water bath. All right. Draw and label the forces that are exerted on the piston. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So I'm not entirely sure what they want here. Do they just want me to say this, the mg of the piston, and then you have the force of the air, of the outside air, and then you also have the force of the inside gas pushing up, because the inside gas is going to push up, and then the outside air is going to push down, and so is the mg. Okay, is that what you want to hear? I hope so. Okay, derive an expression for the internal energy of the gas in terms of m, a, v naught, p atmosphere, and physical constants is appropriate. Okay, so the internal energy. So I know that internal energy is 3/2 pv and 3/2 nRT and 3/2 n capital NKT. I think I'm going to be going with this for the moment. So I know the volume. Okay, so I know the volume. All right, so the volume is already in good shape for me, V naught. But what is the pressure going to be? Well, what I'm going to say here is I am going to express these in terms of pressure. So the F of the inside gas is going to be pressure is force over area. So force is pressure times area. So the force of the inside gas is the pressure of the gas times the area. Okay. And then the force of the outside air, is going to be the pressure of the atmosphere times A. So let's say the pressure of the gas, A, equals the pressure of the atmosphere, A, plus mg. And so then the pressure of the gas is going to be all these guys divided by A. Is A something I'm allowed to have in the answer? Yes, it is. So then this will then be 3/2 and then in the parentheses, P of the atmosphere plus extra pressure added by the piston's weight. The piston's weight adds its own extra pressure. Okay. The block also of mass, a block of M, is placed on the piston at time t naught and slowly lowered. The piston comes to rest at time t final when the block is completely released. Okay. Sketch the expected relationship between pressure P and volume V of the gas for the thermodynamic process that the gas undergoes during time that. Draw an arrow on your sketch to represent the direction of the thermodynamic process. This is a PV diagram. So here's what I'm going to say. The fact that this is slowly lowered means it's isothermal. Why is the slowly giveaway that it's isothermal? Because what's going to happen is that the gas is going to compress, okay? So delta U equals Q plus W. If you compress the gas very fast, then Q does not have time to change. If it's fast, Q needs time to change. So then you'll have positive work done, and positive work means that because the gas compresses, so you get more internal energy, which means the gas gets hotter. So the gas wants to get hotter when it's compressed, but if you do it very slowly, then what will happen is that the gas trying to get hotter has time to send its thermal energy out into the water bath. Excuse me, I'm drinking. These questions drive me to drink. So instead, the temperature stays the same, and you have energy flowing out of the gas into the hot water bath. So this is going to be isothermal. We're going to start with a higher volume, lower pressure, and then we're going to go to a lower volume, higher pressure. Okay. And yeah, so it's just going to be that. So it's going to be like that way. Okay. So this is like T initial and T final or something like that. All right, with the block still on the piston, the temperature of the water bath is changed to a new constant temperature T new. The gas occupies the original volume V naught when the sample of gas and the water bath come to the new thermal equilibrium. So is T new greater than or less than? Okay, so what I'm going to say is I'm going to say this. We're gonna change. So what happened was it was this with no block, then this with the block, and then now this when the hot water bath is actually with the water bath, I should say, it increase. It should actually be hotter. The new temperature should be higher. Okay, so referencing at least one feature of your answers in parts A, B, or C. So what I'm going to say is I'm going to say this. I'm going to say you can either say that the inside gas exerts more pressure, but the same volume. Okay, so if I look at part A, I'm going to say the F of the inside gas is more because the mg is now 2 mg, so so more pressure but the same volume, so PV equals nRT, so more temperature. Okay, so that was the answer there. So if I reference part B, what am I going to say on part B? I'm going to say this. I'm going to say the internal energy is now 2 mg. So now U equals 3 halves P atmosphere plus mg over A, and then it's like two of these, right? Two of these times V naught, right? So more internal energy now. Internal energy is 3 halves nRT, so more temperature, right? More temperature for the gas, right? So more temperature for the water because we're in thermal equilibrium with the water, right? Okay. And then for C, I'm going to say this. I'm going to say the new heating draws a line to the right of T final to a new point above T naught. In other words, it's going to draw this right there. Okay, so that's going to be from this to this is this process right there. It's constant pressure because the same weight is pushing down of the block and the piston, but the volume expands out to the original V naught, right? Okay, so then if that's the case, then so more V but same P for this process, right? So more volume. Okay, more temperature. Sorry, more temperature is what we're going for there. Okay, what do we got going on here? In experiment one, a student is given a resistor of unknown resistance and an air-filled parallel of unknown capacitance. Great, we don't know anything. The student is asked to predict the expected time constant of a circuit if these two circuit elements were connected in series with the battery. They have a battery of known EMF, switch, ammeter, ruler wires as shown in the figure. The plates of the capacitor are square, and the separation between the plates is small compared to the dimensions of the plates. The capacitor is initially uncharged. Okay, assume that the dielectric constant of air is 1. Describe a procedure for collecting data that would allow the student to determine the expected time constant tau. In your description, include measurements to be made, include any, gosh, I'm not entirely sure how I would do this without calculus, because we don't know the resistor. So I guess one way you could do it is maybe we could try to find out what the resistor's resistance is. Okay. It doesn't say that I have to make a straight line graph. Okay, so I guess what I'm going to say is I'm going to say for part A, you're going to measure the length L and width W and spacing D of the capacitor with the ruler. Okay, and then connect the resistor to the ammeter and the battery EMF E in series and record the current I on the meter. It didn't say make a graph, so I'm not going to do repeated measurements or anything like that. But here's what I'm going to say. Calculate capacitance C equals epsilon naught times LW over D, epsilon naught A over D, and resistance R equals EMF over I. That's from Ohm's law. And then calculate tau equals R times C. All right, that's the way I would do it that doesn't involve calculus. Otherwise, I'm not entirely sure how I could do this with AP Physics 2 level knowledge. Okay, in experiment 2, the student is asked to determine the capacitance of a new parallel plate capacitor for each trial. The voltage of the potential difference across the capacitor is varied, and the charge on one plate is measured. So we know that Q is equal to CV. So on the vertical, I'm just going to let that be Y equals MX. Okay, do you see that? So Y equals MX. So the vertical axis is the Q, and the potential difference is going to be the V, right? Okay, and then the slope is just going to be the C. I mean, that's all there is to it. I don't know what else you want from me. Wow, what an ugly graph grid. Okay, so let me put this stupidity in my calculator. Oops. Let me put this stupidity in my calculator. Okay, so they even put it in the correct columns for me, where this is X 3, 5, 7.2, 8, 10. Whoops, that was supposed to go here. Okay, and then 2.4, 4. Oops, 4.2, 5.6, 6.6, 8.0, and then you needed to make sure that all that crap was times 10 to the negative 10. Did everybody notice the 10 to the negative 10? If you didn't, you probably got a ridiculous capacitance. Okay, so good grief, what am I going to do here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Wow, what an annoying thing I have to do. Okay, so how about we do this? How about we go by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is Q times 10 to the negative 10 coulombs. And this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the same thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is V in volts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, this just feels so wrong. Okay, so we're going to go to 3 and 2, 5 and 4, 7.2 and 6. Oh, this just hurts my soul. Oh, no, 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 no. I'm not looking at these correctly. I'm looking at them wrong. It's actually 2.4. Okay, so this is actually about right here. Okay, 4.2. So that's actually more about right there. 5.6 is more about right there. Okay, and then 6.6, 8 and 6.6 lands me about right there. And then 8 and 10. So I just got shafted by the calculator. Okay, so please try your best to look at the pink circled data points, okay? And then this is, I mean, should be no intercepts, so I'm just going to do this. And I might regret this, but let's see. Okay, so let's look at that point right there. Where is that? 11, 12, 12 and a half, okay? Let's come over here, 10 over 12 and a half. So the slope is going to be 10 times 10 to the negative 10 all over 12 and a half. So 10e negative 10 over 12 and a half. And that is 8 times 10 to the negative 11 farads. So that's the capacitance right there, because that was just going to be the slope. The slope is just going to be because Q equals CV. Okay, well, that was pathetic. Okay, two narrow slits are a distance d apart. A screen is a distance L from the midpoint of the slits where L is far greater than D. When a laser emits monochromatic light toward the slits, a pattern of narrow, bright, and dark bands is observed on the screen. Great, great, great. Okay. The centers of the bright bands A and B are indicated. 3 additional bright bands, including a central bright band, are observed on the screen between bands and A and B as shown. Wait a minute. 3 additional bright bands, including the central bright band, are observed on. Oh, okay, so that'd be 1, 2, 3, 4. Okay, great. All right, so the dots are the bright spots. A student claims that the distance between the center of band A and the center of the central bright band is smaller when using a laser that emits violet light than using red light. Okay, now violet light has a lower wave. What the frick am I using that color for? Right, violet light has a lower wavelength, and so let's just go ahead and say this. What is it on the formula chart? Is it d sine theta equals m lambda? But then the sign can be replaced with x over L, where x is the distance from the central bright band to whichever bright you're talking about, equals m lambda. So if you make the wavelength less, then the distance between the dots will be less. Is smaller than when using violet light. And indicate whether the student's claim is correct or incorrect without manipulating equations. Justify your answer by referencing the difference in path length traveled by the light from each slit to the center of band A. Oh my gosh. Okay, so what I'm going to say here is I'm going to say this. I'm going to say the distance D1 from the top slit to A and D2 from the bottom slit to A has a difference delta D, which is D2 minus D1, and that's 2 lambda. Now, what the frick am I even talking about? I'm talking about this distance from this slit here is distance 1, and the distance from here to here is distance 2. Now, these two are different from each other by 2 wavelengths of the light, because this is m equals 0, m equals 1, m equals 2. 2. That means that one path is 2 wavelengths longer than the other one. Okay, now I'm going to say this. If you use violet with smaller wavelength, then the delta D between the paths is also less. The difference in distance is now less. The difference in distance. So the M equals 2 purple spot must be closer to the center in order to make the path length distance delta D less. Yeah, so you had to basically say that the difference between these two paths is two wavelengths, but if the wavelength is less, then this difference is going to be less, and that pushes the M equals 2 bright spot to the center. Okay, derive an expression for the distance between the centers of bands A and B when light of frequency F is emitted toward the slits. Express your answer in terms of all that stuff. Okay, so what did I already say for part B? What did I already say for part B? I said D sine theta equals M lambda, but if L is far greater than D, the L distance, then the sine of theta is essentially x over L. So I'm going to say D times x over L equals M lambda. And now I'm going to do this. I'm going to put a delta in front of the M and a delta in front of the X, okay? So the delta X is what I'm trying to solve for, and the delta M is 1, 2, 3, 4, 4 bright spots, okay? So this is going to be D times delta X, which I'm going to solve for over L, equals 4. Now, what is lambda? Well, the speed of the wave is wavelength times frequency. So wavelength is speed over frequency, and the speed of light is c. So this is now going to become c over f. And now if I solve for delta x, I'm going to get 4 times c, and the L is going to come up. So the delta x is going to be 4c, the speed of light, L, over the d spacing and the f, okay? And then I'm going to say this. I'm going to say indicate whether the expression in part B is or is not consistent. So for part C, we're going to say violet has higher frequency than red, so F in the denominator makes delta X less, which is what I said in part A. All right, well, that's it. That is the AP Physics 2 free response.